E does not stand for energy. E stands for what, Lance? Energy of the photon. Okay, are you with me? There is a difference. I know it's a semantic thing, but this is not a trivial semantic thing. This is sort of a big semantic thing. Okay? If I said E equals mc squared, what does E stand for? That's energy. Okay? But here, it's very specific. It's the energy of the photon. All right? C equals m to 9 nu. C stands for what?
The speed of light.
In a vacuum, which is what?
3.00 times 10 to the 8th centimeters.
No.
Oh, meters per second.
Meters per second. Okay, and it's great that you know the number, but you got to know the units too. All right. So I can use one of these two equations. I mean, those two both have frequency in them. So I should be able to use that to help me get the frequency. What do you suggest?
The speed of light one.
Yeah, the speed of light one. So we know C is equal to lambda times nu. You've already stipulated that this is 3 times 10 to the 8th. So we want to show the formula. We're going to plug our values in. This is 3 times 10 to the 8th. Now, you don't have to do this when you're doing this problem. I'm going to do it because I think it will help you look at it later to see what I want you to see, which is this is meters per second, as you said earlier, right? Mm-hmm. All right. So all I have to do is plug in my wavelength. What do I need to do, though? So the math will work out properly. Pardon me? Well, do you want me to put this number in? Should I put that number in?
No.
Should I put this number in?
No.
What number do I need to put in?
You need to go back to the meter.
There you go. There you go. Do you guys understand what you just saw? In order for you to use this formula correctly so that the math works out, your units have to be in agreement, which means if there's a length unit somewhere present in the equation, anything that has that length unit has to be the same length unit. So if our speed is in terms of meters per second, then our wavelength also has to be in terms of meters. If we use centimeters or nanometers or anything other than meters, this will not work out mathematically. If you want to memorize the speed of light in some other units of length other than meters, if you want to do it in centimeters per second or centimeters per hour, I don't care. It's up to you. That's fine, but your units have to be in agreement for this to work out properly. By the way, if you do use centimeters per hour, your answer won't come out properly in frequency because frequency's units are per seconds. So you'd have to get the hours over to seconds to ultimately give you the correct frequency. Solving this then, I need to do one more step. I need to take our 1.282 times 10 to the negative 4 centimeters. I know there's 100 centimeters for every 1 meter, which means that's 1.282 times 10 to the negative 6 meters, and that's what I'm going to use up here. 1.282 times 10 to the negative 6 times nu. Nu then, when you work it out, 3.2 something, I think. 8 divided by 1.282 6 negative. So you end up with 2.34 times 10 to the 14th as your answer. Is that correct? Are we happy with that, Hunter? Will Mr. Swan give us all the points that we hoped and dreamed for when we do this on the test?
No, it's not labeled.
It does not have the units. That's correct. You must have units. So what are my units? I mean, let's put it this way. If you put the wrong units, I'm going to give you no credit at all. You will lose all the points. All this work for nothing. Units are important on this test. They're important on every test. Because they let me know what you're talking about.
Meters per second.
Meters per second would be the speed. Okay, first of all, this means that you need to know that we measure frequency in certain units, and you don't know what those units are. It's like saying you're 16 miles old. What are you talking about? That is not used to measure time. You're using the wrong unit. You've got to show me that you know what to do. So one thing to do is you're going to have to identify all the variables in these equations and determine what units they're used to express them. The other thing is I want to show you how you can derive this on your own. If you know that you're dealing with C equals lambda times nu, and you know that this is in meters per second, and you've made certain that this is in meters, right? If I solve for this, looking at this for frequency then, solving algebraically, is going to be C over lambda. Can you see that? All I did was isolate the variable. If I now substitute in my units for these variables, so C is meters over second over meters. Do you remember how to simplify complex fractions? Meaning that if you have a complex fraction, I don't know how you guys were taught, but there's little tricks of the trade. Mathematically, it makes sense. I can show it to you and show you how to do it, but very quickly, A over B over X over Y. You can just take the denominator of the smaller fraction and throw it on the other side of the main line. So this becomes A times Y over X times B. Does that sound familiar? Okay. I mean, you can say A over B is divided by X over Y, which you know is the same thing as A over B times the reciprocal of this, Y over B, and you come to the same conclusion. I'm just showing you a quick and easy way of doing that. You take the denominator from a fraction, in a complex fraction, take the denominator from the fraction and throw it on the other side of the main bar. Okay? So coming over here, that means I'm going to do this. I'm going to put this S down here. So this is going to become now M over M dot S. With me? The M's cancel out. So what am I left with?
The seconds to the negative first.
There you go. And that's the units for seconds to the negative 1. Okay, you can use S to the negative 1 or seconds to the negative 1. Or another way of saying that is hertz. Fair enough? So if you do forget, you see how you can derive it yourself and come up with the right answer? That's how you do it. Questions at all? All righty. Okay, so let's go on and do the next one, number 5. Give the name of the central concept of the foundation of quantum theory and summarize what it says. All right, Chaitanya.
The central concept of quantum theory is wave-particle duality.
Good.
This means that in some ways EMR behaves like continuous waves, and in some ways it behaves like individual particles, and then again, in some ways. In some ways it behaves like individual particles, in some ways it behaves like waves.
Okay, you're missing something there.
Yeah.
Okay. Wave-particle duality, okay, suggests the wave-like nature of things and the particle-like nature of things. There are two sides of the coin, though. One deals with EMR. You mentioned that. Energy, okay, EMR. Energy can be particle wave-like in nature, but at other times it can behave as if it were, it can be wave-like in nature, but at other times it can behave as if it were particle-like in nature. Matter is the part you're missing.
Yeah.
Matter,
Couldn't read it.
okay, so if you can't read it, I can't read it. Okay, you guys have got to write, so if you can't read your writing, I'm going to have issues. So you just on the test, make sure I can understand what you're trying to say. Matter can be particle-like in nature, and at other times it can be wave-like in nature. We're going to look at that part of wave-particle duality next. That's the other side of the coin to quantum theory. So far, you and I have only looked at the wave-particle duality of energy, or EMR. Questions on 5? In number 6, it says, what does it mean if we say something is quantized? Michael, what does that mean?
is restricted to amounts that are multiples of a basic unit or quantum for the particular series.
There you go. So in our example with ice cream, our ice cream was restricted to basic amounts called scoops. Okay, you couldn't just lick it or take half scoops. A step ladder would be said to be quantized with respect to steps. You can take 1 step, 2 steps, 3 steps. You can't take 3.5 steps on a step ladder. Make sense? Okie doke. In number 7, you had to define each of these terms. Do you want clarification or verification on any of these terms? Yes.
Threshold frequency.
That's simply the minimum frequency of a metal necessary to display the photoelectric effect, yes. The minimum frequency necessary for a particular metal to display the photoelectric effect. And different metals have different threshold frequencies. Why, Eric? Why do different metals have different, why don't they all have the same threshold frequency? For instance, potassium has a different threshold frequency than sodium.
They have a different system of. No, that's
Jacob, how come?
because they have a different amount of photons.
So,
Does that give them a different amount of electrons?
so, I'm not disputing what you're saying. I mean, everything you said is fine, but I just don't understand.
Does that somehow make them able to use different energies of photons?
What do you mean? I don't understand.
Like, does that make it so that they can use, like the electrons can use different energies of photons to come off?
Well, okay, a threshold frequency is the minimum frequency a metal must be struck by in order to get the photoelectric effect, right? If I'm saying that I have 2 different metals and they have different threshold frequencies, I want to know, well, why would they have different threshold frequencies?
It's because in some the electrons are more strongly attracted to the
That's the answer. Okay, that's the answer. Some metals hang on to their electrons more strongly. The nucleus has a better hold, so you got to give them more energy to get them off. It's as simple as that. Eric, make sense? Questions at all? Joe?
With the definition, the minimum frequency that below which the photoelectric effect does not happen.
That's fine.
Particular metals are-
That's, you're saying, yeah, it's just 6 of one, half dozen of the other. Saying the same thing. Questions? Any other questions concerning number 7? Okay, in that case, number 8, you had to go ahead and give Planck's equation and identify what the variables were and explain its significance. So, all right, Ada, you're up. What's Planck's equation?
So E equals H times nu.
Okay, tell me what these variables represent.
So E is the energy of a photon.
Good job, yes. H
H is Planck's constant.
and nu.
Nu is frequency.
Okay, good. That's, so we know what the formula is, we know what the variables represent. So what? What's the big deal about it?
Well, when radiation is emitted, transmitted, and absorbed in quanta, it's emitted, transmitted, and absorbed in quanta, that's determined by the frequency of the radiation and the value of Planck's constant.
Okay, you are giving me the implications of this formula from its inception when Planck first introduced it. What I want to know is, what is the significance of Planck's equation today, now that Einstein has added to what Planck already had said? Do you understand?
Okay.
So in other words, I want you to look at this from the big picture as of today, why is this important? Not according to what Planck was saying. It has bigger implications than what Planck had originally stated. You understand what I'm looking for?